Okay. That's okay.
Ah, sí. Sí, no tienes interferencias, no, as you should.
We're going on with our next talk, and I'm very happy to welcome Mariano here. He's part of our BeFEMTO project, which is a project, IP project, very large project dedicated to the design of femtocells. Now, he's the leader of a fairly physical layer-oriented work package, really, and so we have him here today to give us an overview what are the real hardware challenges to design essentially femtocells. Now, Mariano works for TTI, which is a fairly big company in Santander and Cantabria, and the floor is all yours.
Thank you very much. First of all, I want to thank all the CTC people for organizing this nice event, and especially to Misha for inviting me to make this presentation. My name is Mariano Lopez, and I work for TTI, that is a SMA, a Spanish company that is placed in Santander, Cantabria, that is placed in the north of Spain. Now we are about 100 people that works mainly in Santander and also in Madrid. Some people is working in Madrid, but okay. Our main business is dedicated or is the developing of radio frequency and antenna hardware. We develop nearly all subsystems of radio frequency field, like low noise amplifier, high power amplifiers, frequency converters, mainly customized on for the customer requirements. Also, we develop and design an electronic antenna with electronic pointing system and electronic tracking systems, and this is our main business. Okay, in this talk, I will talk about the challenges that you can find in designing the femtocell LTE-Advanced hardware. Okay, I have organized this talk in several parts. First of all, I would like to make a short overview of the femtocells. I guess you know very well. Also, I will like to take a light overview also for the LTE-Advanced standard. And the main core of the talk will be devoted to the femtocell design challenges. We will focus this problem on four main points, on four main aspects, like the mass production aspects, the technical requirements for LTE-Advanced that is very challenging, the carrier aggregation feature that is, I think, one of the most important characteristics of feature technologies for the LTE-Advanced standard, and finally, with the available technology developed currently by manufacturers. Finally, I would like to show you how is more or less the inside the femtocell, and we will try to identify more or less the most important parts of femtocell hardware. Okay, femtocells. The first part is a light overview of the femtocell. Femtocell, as you know, is a small and low power cellular base station which connects the user or several users to the operator using a broadband connection. In other words, this is a device mainly devoted for indoor environments like residential or even company environments, which is connected to a DSL or cable connection, and that routes all your cellular devices that you can have, for example, at home, like the mobile phone, the TV, the laptop, all of devices that you can imagine, and routing this traffic for through a DSL connection. This kind of devices presents several benefits, but also comes with a subset of challenges for developing these benefits. For example, one important benefit that provide this kind of devices is that due that is intended for indoor environments, these kind of devices provide improved coverage in indoor devices that macrocell cannot assure, and also for the capacity too. This is very important for the macrocell because in the macrocell you can experience problems with attenuation loss and things like that. But in indoor environments, it is a very good solution for fulfilling this coverage and capacity, for improvement these coverage and capacity terms. This kind of devices also provides or also allows to offload some traffic from the macrocell, because if there are a massive deployment of this kind of devices, all of the traffic generated at home can be routed through these devices, alleviating a lot of the macrocell problems with the traffic. And for the operators, it's very, very attractive with this solution because due to the two main points, they can have reduced cost for these deployments. But this benefit comes with several challenges. The most important challenge that you can find, in my opinion, is the interference management. This is a small base station, and it radiates and also receives signals, radiated signals. So, if they can provide interference to the macrocell, and also it can receive interference problems with macrocell. If it's also several femtocells in one building, also they can suffer interference between femtocell. So in this way, the interference management guys have to face the problem with macrocell and femtocell interference, and also between femtocells. Another challenge to be developed, to be faced, is the cost of these kind of devices. These are high technology devices, and when you pay for high technology, normally the cost is very high. But if you want to make a massive deployment of these devices, this has to be reduced. So it's a problem, and it's a challenge that has to solve the technology. And also, from the point of view of the operator, it's a problem to integrate these devices for the interference issues that I have talked about. Okay, this is more or less regarding the femtocells. Let's see a little bit what is LTE-Advanced. LTE-Advanced is the evolution of the next generation standard communication, that is LTE. And it has been defined by ETUR in order to have bigger targets in some points. For example, it has been defined a peak data rate target of 1 gigabits per second in downlink and up to 500 megabits per second in uplink. It also be defined a peak spectrum efficiency higher than specified in LTE. For example, 30 bits per second per hertz in downlink and 15 bits per second per hertz in uplink. It has also been defined to have a lower delay in control plane with the same specification in user plane than in LTE. And one of the most important characteristics of LTE-Advanced is that the bandwidth to be handled is defined up to 100 megahertz in order to reach the peak target data rate. In LTE is defined up to 20 MHz, but in LTE-Advanced is defined up to 100 MHz. That is a problem for the technology point of view. In order to achieve these targets, it has been defined several features in LTE-Advanced. For example, carrier aggregation is defined as a main technology in order to support the wider bandwidth up to 100 MHz. With this feature, it could be achieve an improvement of the peak data rate of up to 1 gigabits per second in downlink. It also has been defined advanced MIMO techniques up to 8 layers in downlink and up to 4 layers in uplink, and this will make an improvement of peak data rate and also in capacity terms. And finally, it has been defined several more features like the coordinated multi-point transmission and resection that will provide an improvement on throughput and coverage, further reduction of the delay in quantum plane before presented, and also on relaying that will provide an improvement on coverage and flexibility of service. Okay. LTE-Advanced has been another challenge that has to face is in which frequency bands has been going to deploy. This is a very hot topic also for LTE, for the current LTE network that has been now has been implemented because you have a lot of problems with the spectrum, and this problem is different in different regions. So 3GPP has defined several possible candidate bands, and it will be analyzed in further meetings, I think, in order to analyze this kind of deployments. But in this deployment, depending on this deployment, the technology has to cover different bands. So it's very, very interesting and very important topic on the LTE-Advanced and also on LTE terminals. Okay. LTE-Advanced is being standardized on release 10, and this is made by the 3GPP partners. Here in this slide is presented several important requirements, but the most important is that LTE-Advanced is studying in the 36 series of technical reports and things like that. There are hundreds of documents regarding the specification requirements and specifying all the LTE technology. Okay. This is all for LTE-Advanced, a short overview. Okay, in next slides, we are going to face the challenges for the femtocell design. Okay, this is a femtocell hardware overview, more or less, a typical femtocell. In this part, you can see all the DSP. The digital processing that was presented before for the digital processing. This part we are going to focus in this part. That is the hardware. In this part is deliver the bits, and we are going to translate the radio frequency signals. Okay, this part. This is a transmitter. This is a transmitter, and this is a receiver part. And also, you can find here also the power supply part that fits all the circuitry related to the femtocell. Here, there are the antennas. This is a FDD femtocell because it employs a duplexer here. And okay, this is more or less the part that you can find on a femtocell hardware. Okay. how we can face how are the challenges that we can find on the design of the LTE femtocell hardware. First, we can talk about, for example, the mass production aspect that is very practical issues. The LTE-Advanced requirements will present another set of challenges for this design. The same for carrier aggregation, and also with the available technology will present the most important circuitry that you can have available in order to design this part. Okay, we are going now to see more or less in deeper each one point of view. In the mass production aspect, that it has to be taken into account, for the femtocell deployment, you have to take into account three main aspects, that are the low cost, the low size, and the low consumption. That is very important, the three of them. The low cost, because you have to success of the massive deployment, so in the, you don't have, you have to design cheap solutions, very cheap solutions, in order to have a competitive product. After that, you have a low side, because these are very small devices. You can develop a high device, because it's not feasible to sell, and this leads to use high integrated devices. Some of them are available from the manufacturers, from the chip manufacturers. And finally, you have to design taking into account a low consumption, because now we are developing green networks. So this is also a good, important point of view. Okay, you have to take in mind these three aspects in order to design the hardware of the femtocell. LTE-Advanced requirements. The LTE-Advanced requirements presents several challenges. We will see. We will see how far they are. There are these requirements on LTE-Advanced you can find on 3GPP series, in the 36 series, and I have put on this table a summary of some important parameters that you can take into account in order to design a femtocell, or to have in mind if you want to design a femtocell. These technical specifications are mainly divided in three main categories regarding the component carrier aggregation, the transmitter, and the receiver characteristics. Regarding the component carrier aggregation, you can the most important is you can find the channel raster, that is 100 kilohertz. This is the step that you can find for the frequency development. That means that if you want to transmit one frequency, it has to be a multiple of 100 kilohertz. That's very important. The channel bandwidth, that is scalable, like in LTE, like is defined in LTE. And for the transmitter characteristics, we are going to go in next slide deeper one by one. Okay. In this slide, I present the basic scheme of a transmitter. The most common, this is a direct conversion transmitter, which is the most common architecture used for mobile and cellular devices. In this transmitter, you can find the digital to analog converter, which conforms the baseband signal. This baseband signal is delivered to a mixer that translates directly with the help of the local oscillator to the RF carrier. That means that the frequency of the carrier is the same that the local oscillator. Okay, this is the reason why it's called direct conversion. After the signal is produced in the mixer, is filtered. Is filtered because you have to take very care of avoid unwanted emissions in order to not interfere another systems, and finally is amplified with the proper level in the power amplifier. With this arrow, I want to point which part of the transmitter is responsible or has a contribution on the different requirements of the LTE-Advanced. For example, these three parts are responsible or have contribution on AC LR, adjacent channel leakage ratio. This part is responsible for the phase noise and also for the frequency error. And these parts are the power amplifier, the mixer, and the local oscillator has contribution for the error vector module. In next slide, we can see one by one these kind of requirements. For example, the frequency error. What is the frequency error? The frequency error is the difference between the femtocell transmit frequency and the assigned one. For example, if you want to transmit at 2 GHz exactly, if you transmit at 2 GHz and 1 MHz, you have 1 MHz of frequency error. That's a problem. That's a problem because the synchronization and the frequency accuracy in femtocell is a big challenge. The main responsibility for this frequency error is devoted to the clock, to the reference. That is a very accurate reference signal. And if you have a bad frequency error, the impact is the loss of the orthogonality in the received carrier frequency. For example, you can see in this figure. If you want to transmit, this is a QPSK signal, the constellation. If you want to transmit this part, these symbols in red ones, if you have a frequency error, if you have no frequency error, you transmit this exactly these 4 points. But if you have frequency error, the constellation rotates, and you can see what is the effect. That provides an increment of bit error ratio. So you have to take care with this requirement. And the design challenges, if you have to be on fulfilling the requirements for LTE-Advanced, you have to use a high accuracy and stability reference. But it's a problem because these kind of sources are very expensive. For example, if you use an open control crystal oscillator, you can pay, for example, 1,000 euros, and it's out of scope here. Now, with the current, some manufacturers have developed very cheap crystal oscillators, about 5 euros, with that are in the target of LTE-Advanced requirements that are 0.225 ppm, plus minus. And also sometimes are used several techniques in order to compensate these errors. Okay, so this is important parameter. Another important parameter is the phase noise. Sorry?
Question on previous slide. Does this phase shift only come from the frequency error or also from the nonlinearity of power amplifier?
Well, in this part, the frequency error comes. The phase is more or less the same, but in this part, the frequency error provokes these effects. You can have also in the error vector module due to nonlinearities of the amplifier, and also of quadrature mixer or some part in the chain that are non-linear. We are going to see the error vector module in one slide. Okay. Another important requirement is the phase noise. The phase noise is the main characteristic of the local oscillator, that is a part of the transmitter and receiver. The local oscillator is a device which generates a fixed signal. Ideally, you have a delta, the Dirac perfect, but this is only ideally. In real world, you have this kind of noise that is called phase noise. Okay. The better low phase noise you have, the lower skills you have, and it's very important to design with care this part. The impact of have bad phase noise is the increase of the error vector module. Also, you have problems with the sensitivity, because if the skills are very wide, you can have problems on this. And also the increment of the bit error ratio. If you want to have no problems with this part to fulfill LTE-Advanced requirements, you have to design low phase noise oscillators. That is a challenge because it's also be defined higher order modulations that requires also good phase noise, and also a very low frequency step size that is against the phase noise. So this is another challenge. Fortunately, this challenge is solved, but it's a challenge. Okay. Next parameter you can see on a transmitter is the error vector module, that is defined as the vector difference between the ideal signal and the measured one. As you indicated previously, if you want to transmit this symbol, if you have an error vector module, the symbol is here. So this part is called error vector module. It is normally measured in percentile of RMS. We have several contributions for the error vector module. For example, the local oscillator can increase this requirement. The IQ measure can increase, and the power amplifier. That this is related with the linearity of this amplifier. If this amplifier is not linear, you can have a lethal increase of this number. For example, you can see here. For example, this is a typical high power amplifier for LTE with 64 QAM, and this is the output power. For example, if you see if the amplifier works here at this power, there's no problem. You don't have any problem because the maximum allowed in LTE is 80%, more or less, if I remember well. If you increase the output power, you can see how is increased the error vector module. And for example, this amplifier, I don't know if output power, I guess will be around 20 dBms. You can see here, it increase dramatically. So you have problems on here. So in this, for example, for fulfilling LTE-Advanced requirements, you can work up to, I guess, 16 dBms in order to have, let's see, if I remember well, it's 8% specification for LTE-Advanced. Okay. If you want to have no problem with this, you have to design low phase noise local oscillator that is in line with the previous slide. You have to have a balanced IQ modulator in I and Q branches. The I and Q unbalance also can provide problems on this parameter, and the mainly contribution is the power amplifier, the linearity. Okay. Another parameter interesting and to have into account for the design of RF part transmitter is the adjacent channel leakage ratio. It's called ACLR. This is the ratio of the between the transmitted power, that is, and the power transmitted and in the adjacent channel. That is, the main responsibility for this is the field filters in the digital domain, but mainly the power amplifier, because the target is to work the more as you can. The output power, it has the power amplifier, but if you work very near, you can experience problems with this. Also, like in the error vector model. For example, this is an example of LTE amplifier. I guess is the same that I presented before, and this is the specification for LTE. You can see the LTE spectrum, and this is the ACLR in the adjacent channel. I guess it fulfills the specification, but this is an example. Okay. You have to take into account also this parameter.
Sorry, I just have a question on previous slide. Compared to the macro base station, femto base station is supposed to transmit on very small power, low power. So does it help in avoiding the nonlinear region of amplifier, because you can operate on?
Yeah, you can operate, but in this case, you are going to operate with lower power amplifier, for example.
Okay.
On BeFEMTO cell, the maximum output power, for example, in BeFEMTO is the target is 10 dBms.
Mm-hmm.
But for example, I guess with a power amplifier up to 20 dBms, it has to be enough. But if you work with lower power, with an amplifier with lower and 1 dB compression point, you can have problems on this.
Problems, okay.
So mainly is devoted with the difference between the back of difference.
Back of, yeah, yeah, okay.
Okay, another important problem or a requirement to have into account is the unwanted emission. As its name indicates, is all the signal that you don't want to emit. And in any transmitter, all of this dirty spectrum is mainly created in the mixer, in the frequency mixer, IQ mixer in this case, and also in the amplifiers due to nonlinearities. Okay, so you have to employ in order to reduce as much as possible this effect. You have to employ very good IQ modulators with high sideband suppression band, and also with low carrier feed-through. There's a parameter how is isolated the local oscillator, and you have to employ high selectivity filters. High selectivity filters, as the previous technology, if you want to employ high selectivity filters, they size increase. So, but more or less, there are a massive production on filtering, and more or less is solved. You can find in 3 by 3 millimeters very good filter stages that rejects a lot of unwanted emissions. Okay. This is a simulation that we made for one LTE carrier, 20 megahertz. This is for transmitter chain. This is the signal that you can have with ideal transmitter, with no impairments, absolutely. And this is the real simulator spectrum, including all of these impairments, the phase noise, the 1 dB compression point, and things like that. So you can see how is increased the spectrum. This is noise, and this is the adjacent channel leakage ratio. In this simulation, I guess, is fulfill the LTE-Advanced requirement, that is 45 dBs for the adjacent channel? I guess yes, because it has to be fulfilled with minus 65 dBms. Okay. So this is, you can see, it's interesting because you can see how is degraded the signal, the LTE signal, due to the transmitter impairments. Okay. Now we are going to analyze the receiver. The receiver is has the opposite block diagram than the transmitter. In this is use the direct conversion architecture, that the signal that comes in RF frequency is translated directly to baseband signal with the help of the local oscillator that has to be in the same frequency of the transmitter in order to tune perfectly the signal. In this transmitter, we can see the band filter that rejects all interference and non-desired signal and other services. The low noise amplifier that is has a lot of responsibility on the sensitivity of the receiver. The quality mixer and the filter and stages for the baseband in analog to digital converter. It also has been represented the main parameters and which are responsibility, which module has responsibility on each one. Okay. In this way, the phase noise is the same rationale that in the transmitter case. So there's no more space. And we are going to see the sensitivity and also the adjacent channel selectivity. The sensitivity is defined as the smallest radio frequency signal that can provide useful and usable baseband output from a receiver. The responsibilities on here are the low noise amplifier, mainly by its noise figure and the gain, the radio frequency filter stage by its filtering and also by its losses, the IQ demodulator, and also the analog to digital converter. If you have a bad sensitivity parameters, you will suffer of a poor coverage. There is a problem on femtocell because in femtocell the target is to transmit with low power. So it's very important to have a very good sensitivity term on the receiver. Okay, and if you want to have a good sensitivity, you have to design a low noise amplifier with a low with low noise figure, and also with high gain in order to isolate the rest of the contribution of the noise figure of the rest of the parts. Also, you have to use a low RF filter, low losses RF filter, because the losses of this filter goes directly to the noise figure and goes directly to sensitivity. You have to choose analog to digital converters with a high dynamic range in order to handle low power signals, and low imbalance IQ demodulator that is very common to the transmitter part. In this way, it's a IQ modulator, and this part is IQ demodulator. Okay. And the last one parameter that we can take into account is the adjacent channel selectivity. That is a measurement of the receiver ability of working with a strong interfering signal. Okay. In this way, if you want to have a good parameter on here, you have to employ very good filtering stages in order to reject possible interfering signals. And also, you have to work with a low noise amplifier with high point compression in order to handle strong signals. Because, for example, if a low noise amplifier has a low power compression point, if it receives one strong signal, it could be saturated, and it causes a lot of problems on the receiver by generating of several intermodulation products and things like that. So it's another important question on this parameter. If you had a bad number on this part, the problem is the degradation on the receiver performance. It's clear. Okay? And if you want to have, as I previously commented, if you want to have a very good behavior on this part, you have to use high selectivity filtering stages and high linear amplifier stages, mainly in the low noise part. Okay? This is regarding the LTE-Advanced requirements, the most important. Another issue that is very important and is a very characteristic of LTE-Advanced and on LTE-Advanced is the carrier aggregation. It is mainly also it's a requirement, but I want to separate because it has another impact on the architecture and the hardware design on the Femto. Okay, what is the carrier aggregation? The carrier aggregation is a technique that able to handle the support the wider bandwidth transmission up to 100 MHz by supporting several LTE channels. One key requirement on LTE-Advanced is that it has to be backward compatible with LTE. What does it mean? That means that if you have LTE terminal working on LTE-Advanced network, it has to work. And also, if you have an LTE-Advanced terminal on an LTE network, it has to work. So in this way, the solution is to handle the aggregating the 100 MHz bandwidth by aggregating 5 LTE carriers of 20 MHz. And how is aggregated? Well, 3GPP defines 3 main scenarios for the carrier aggregation. The first one is the contiguous intra-band carrier aggregation of the 5 component carriers. If you have, this is the easier way to aggregate the bandwidth, but the problem is you have to be available with 100 MHz in the spectrum. That is a problem. Mainly regularity parts. It's a problem. It's not easy to find 100 MHz in the spectrum. Another scenario, the second scenario that handles the 3GPP is a non-contiguous intra-band carrier aggregation. For example, if you have available 80 MHz, but only you can develop 60 MHz, for example, you can put 20 MHz here, 20 MHz here, and 20 MHz here, but in the contiguous band, 80 MHz. Okay, this is more or less the idea. And the third one, that is, I guess, the most possible and the most challenges, is the interbar carrier aggregation. The interbar carrier aggregation means that if you want to fulfill the 100 MHz, the most likely scenario that you can find is that you can have, for example, 40 MHz at 800 MHz band, 40 MHz at 2 GHz part, and maybe 20 in another part of the spectrum. That means that you have to generate all these signals in several parts of the spectrum. That is the most challenging part.
LTE put a limit on this interband carrier? Means at the most you can have only 2 carriers, or you can have 5?
You can have more. This, I guess this is a figure in order to present, for example, only 2 component carriers. But for example, the idea is if you have, for example, 40 MHz in 8 MHz in 800 MHz band, 40 MHz in 2 GHz band, and 20 MHz
somewhere else. Okay.
And somewhere else.
So
the idea is
standard allows for that.
Yeah.
Okay.
Yeah. Well, 3GPP, In this way, the 3GPP has studied several scenarios and have proposed 4 main scenarios for ITU submission up to now from NEOS. The only part that is covers the 100 MHz part is this scenario, that is the single contiguous band at 2.3, from 2.3 to 2.4 GHz on TDD, TDD duplex scheme. This is only the 100 MHz, the full 100 MHz that is studied currently in 3GPP. Okay, and this has a very strong impact on the design. For example, if you employ a contiguous aggregation, you can employ, if the technology allows, I think it allows. For example, if you want to handle 100 MHz, you can use, for example, only transceiver with wider elements, 100 MHz of bandwidth, 100 MHz of bandwidth, and 100 MHz of bandwidth. If the technology allows, you can employ only one transceiver. That's okay. That is the easiest way to deploy and the cheapest way to deploy this part. For example, if we go through intra-band carrier aggregation, also we can make an hybrid solution. For example, if we can handle we can multiplex, for example, in this we can multiplex this part in baseband and this part using only one transmitter with only one local oscillator. You can make it. Okay. But if you have interval aggregation, the most likely solution is to employ one transceiver per band, because it's not easy to, for example, mainly in baseband, to put, for example, one of the deployment in Europe are, for example, an LTE is 800 MHz and 2.6 GHz. That is very far. So you have to employ for example, two transceivers. And if they are separated more, you have to employ up to 5 transceivers. That is very complex to integrate with with low cost and low size. So this carrier aggregation has a great impact on the design of the hardware of the FEMTO. Okay.
I see in this interband still you are sharing the RF power amplifier.
Yeah, this is if the power amplifier, for example, can handle
100 megahertz in different bands.
In different bands, you can also employ, but if it's not, you have to employ different chains, different power amplifiers, and also it's the same for the receiver.
Yeah. So means I'm trying to understand, does the state-of-art power amplifiers allow to amplify a signal on 800 and 5 gigahertz at the same time?
Yeah, there are developed several power amplifiers that works from, for example, 500 megahertz up to 3 gigahertz without problem. And with a different compression point, but fulfilling the LTE-Advanced requirements. Okay, but if the power amplifier is such a wide band, there is going to be intermodulation products, yeah? Yeah, you have, okay. And then if you have a wide band filter as well, so how it's going to filter out those intermodulation? The filtering can be handled by here, for example. Okay. If you filter here one band and you filter the other band here, in principle, if you zoom, there's no problem. But you have to take into account all of this in the architecture design, because you can find problems. For example, if you can multiples of the local oscillator put on here and things like that, and interfering one transmitter to another transmitter. But in principle, if you filter here after the IQ measure, you have no problem. Okay. Okay. And this is a simulation example that we make on BeFEMTO on the deliverable the 3.1. That is okay. We zoom in the scenario, in the 100 MHz scenario, 2.3 to 2.4 in TTE. We generate five carriers, 5 LTE carriers, and finally, this is with ideal transmitter, something like that. And in here is, you can see the contribution of the impairments of the 5 transceiver. This was simulated with 5 independent carriers sharing the power amplifier, for example, because power amplifier could cover the 100 MHz band without any problem. But using 5 independent carriers, 5 independent transmitters. Okay, and also is this is fulfilling also the 45 dB for ACLR. Okay. Okay, and finally we can take a look on the available technology that you can find for developing this part. For example, this is single devices. You can see the aspect. This is very small devices. For example, this is a duplexer that I think is LTE, but 2.5 to 2.6 gigahertz. This is the band 7, I guess. This is, for example, a power amplifier in 3 millimeters by 3 millimeters, the size, 27 dBms. And this is another LTE power amplifier of 30 dBms, 1 watt. In 3 millimeters, I guess 4 by 4 millimeters. I don't remember well, but you can see single devices, examples. This is more integrated solutions. For example, in this chip, you can see a transmitter, a receiver, and a transmitter integrated with several functionalities. I don't remember the size of this, but it's not bigger than 6 by 6 millimeters. So the integration scale here is very high. This is another example with a transmitter, a receiver here, a transmitter here, and a receiver here. Also with the control channel, control signal, and things like that. Also, is very good integrated. It's from Lime Microsystems. We can see another more integrated device. It integrates local oscillator, filtering. It integrates a transmitter, a receiver, with filtering, with local oscillator, with amplifiers, with control signals, and things like that. Also, is LTE transceiver that cover this band and is placed in 6 by 6 millimeters. And now is also is being developed this part, but with MIMO 2x2 chips. So this is crazy for measuring, for soldering, but it's very good integrated. So a technology is updating these kind of devices, and the scale of integration is amazing. Okay, and lastly, I will take a look for a femtocell. That is a Cyan femtocell. If you open a femtocell, what do you see? For example, in this part, you can see all the DSP parts with memories, with switch, Ethernet port, and things like that. This is also part for the DSP part. The antenna is placed here. This is a printed antenna. This is only with a single antenna here. This is the power amplifier, you can see. This is the RF transmitter. This is very integrated, like I presented before. I guess I use this chip for Maxine, the transmitter, but only transmitter. This is the receiver. And you can see this is the crystal oscillator that has a TCXO. And this is on the size more or less here. You can find this here. This is a Cyan femtocell, and more or less if you open a femtocell, you can find this. The problem, I guess, it will be when you want to implement the 100 megahertz bandwidth, and also you want to employ MIMO schemes. For example, 8x8 MIMO schemes, now I don't see very feasible, because the space is very limited, and there's problem. I think it will be problems. The MIMO in femtocells, I don't know up to which layers is going to be implemented.
So for 8x8 MIMO, let's have an RF chain for each antenna?
Yeah. You have to employ, you have to
8
multiply by 4.
By 4. Okay.
And for example, if you have 5 transceiver, 4 by 5, 20 transceiver. That's a problem of the size. Well, it depends. If you have a bigger house, no problem.
So I have another.
Okay.
So I'm aware like there are some research doing like the RF impairments. They are trying to do it in the DSP or the baseband.
Yeah.
So I need to know which of these RF impairments like people are trying to solve in the baseband rather than the RF.
Well, let's say for example in this part, I guess the power amplifier goes out, and this is used, for example, like here, power amplifier. Low noise amplifier also goes out, and they use very linear technology because they handle very low power signals. So this is the idea of integrate this digital part with the analog part. They handle very low power signals, and I think it can be solved very good.
Thank you.
Okay. In conclusions, the last part of the presentation. Okay, the LTE-Advanced presented a lot of challenges. I will name problems for hardware designers. The carrier aggregation also has a very great impact on the hardware design. And the strong specs defined on LTE-Advanced comes once highly narrated for all the components, improved sensitivity for the receiver, lower phase noise, wider bandwidth components, and also with lower cost, size, and consumption. So this is the problem, the challenge will be faced by technology, and I think it will be solved, but I don't know when. This is the reference I put. This is. Thank you for your attending.
Okay, so Misha couldn't make it for the end of the presentation, so I will be handling the closing of the presentation. Are there any more questions from the audience? Okay, I have one. Among all these challenges that you described, which one do you think is the one which will have the most difficult to be solved?
For me, it's the carrier aggregation. The carrier aggregation because it's, for example, in all the requirements on the transmitter can be solved more or less. But if you want to employ, for example, 5 LTE transmitter or 5 LTE receiver, the problem is the space and also the consumption. So I guess the main problematic issue is the carrier aggregation.
Okay, thank you. Any more questions? Okay, so let's thank the speaker again, please. Are you aware of, like, for lunch or this kind of issues? I'm not sure. Like, Misha didn't tell me about the schedule, so